Okay, let's get started. Good afternoon, everyone. Welcome to this discussion section. Today, we will work on several problems related to relations, functions, and combinatorics. So let's get started with the first one. Let's firstly use 2 minutes to think about it, then we will work on it together. Okay, first, we need to show this function is one-to-one. If we want to show a function is one-to-one, we need to prove that if two function value is equal, then the two input should be equal. So we can assume f(a1), b1 is equal to f(a2), b2. And we need to show a1, b1 is equal to a2, b2. This is the main idea of proving the one function is one-to-one. So we have the rule of this function. So f a1, b1 is equal to 2 to the power of a1 times 3 to the power 1 of b1. And we also have f(a2), b2 is equal to 2 to the power of a2 times 3 to the power of b2. And we know the two function value is equal, so 2 to the power of a1 times 3 to the power of b2 is equal to 2 to the power of a2 times 3 to the power of b2. This is by the assumption. Then we need to do some algebra on these functions. We can move the right-hand side to the left, and we get we get 1 on the right-hand side. And rewrite the left-hand side, we have 2 to the power of a1 minus a2 times 3 to the power of a1 minus b1 is equal to 1. And then 1 is equal to 1 times 1. So it is equal to 2 to the power of 0 times 3 to the power of 0. Now we can get a1 minus a2 is equal to 1. a1 is equal to a2. and B1 minus B2 is equal to 0. B1 is equal to B2. So A1, B1 is equal to A2, B2. Therefore, F is 1 to 1. So we are done with this proof. Any questions so far? Okay, let's go to the second sub-question of this problem. So we need to prove the function is onto. If a function is onto, then when we pick a element from the codomain randomly, we can always find a element from the domain that the f of this element is equal to the element you picked from the codomain. So if we want to prove f is onto, we can assume we pick items from the codomain. The codomain is B. We can assume C from B. Then we need to show we can find elements. I use A, B from the element A such that FAB is equal to C. So this sentence is the main idea to prove that the function is onto. There is a hint that the primary factorizations of 144 is equal to 2 to the power 4 times 3 power 2. So since and C, and because C is an element of N, so C is a positive factor of 144. And by the definitions of a positive factor, we can have C is equal to 2 to the power of x times 3 to the power of y. Where x is an element from 0, 1, 2, 3, 4, and y is an element of 0, 1, 2. So any question about this statement? So we already know the prime factorization of 144 is 2 to the power 4 times 3 to the power of 2. Then if we choose an element, if we choose a factor of this number will this factor must be in this format. And because it is a positive factors, so x should be in the range of 0 to 4, and y should be in the range of 0 to 2. And this means fxy is equal to 3. Now we have proof. Now we proved given an element from the codomain, there exists xy, which is an element of the domain, such that fxy is equal to c. And this means f is onto. Okay, any question about this problem? We are done with this small sub-question. Great. Let's go to the question C. So in this one, we needed to use parts A and B, and show the cardinality of both A and B. So in this question, we need to use theorem 7, which is on page 292 on the textbook. So by theorem 7, from part A, we show the function is 1-to-1. So NA is smaller or equal to, the cardinality of A is smaller or equal to the cardinality of B. You can get this conclusion directly from theorem of 7. And from part B, F is onto. So NA is larger or equal to NB. Thus, we have the cardinality of these two sets is equal. For set A, we have 0, 1, 2, 3, 4 cross 0, 1, 2. So the cardinality of this one is the element of the first part times the element of the second part. We have 5 elements in the first part and 3 elements in the second part. So NA is equal to 5 times 3 is equal to 15. And because the cardinality of these two is equal, so NB is also equal to 15. We are done with this part. Any questions so far? Great. Let's go to the next one. In this one, we need to decide if the relations is reflexive irreflexive, transition, and antisymmetric. So we will. So please use 2 minutes to think about it, and then we'll work on it together. And I will write down the mathematical definition of the function as well as these properties as well. So the first one is reflexive. Okay, let's get started with relation 1. So you can type your answers of R1 in the chat and tell me if there are yes or no, they are reflexive. Okay, there's an answer no. That's right, because no letter is immediately precedes themselves. So the second one is whether or not that they are irreflexive. Okay, yes. And the reason is the same with the previous one. And the third one is whether they are transitive or not. Okay, someone says yes, someone says no. The answer is no. Because remember, in this relation, we needed to immediately precede, alpha should be immediately precede beta if AB is in this one. So for the letter A and B, because A is immediately precede of B, so it is in R1. BC is in R1 too, but AC is not in R1 because A is not immediately precede C. Okay, here is a problem. Can something be neither reflexive or irreflexive? Yes. For the reflexive, it requires all the elements have these properties. And in irreflexive, it is also requires all of them to be. So let me think about an example to show that. Okay, I will think about it later. Oh, thank Peter. He answered it. If some reflect back and others do not, then it is neither reflexive or irreflexive. Yeah. Let's go to the antisymmetric. So do you think R1 is antisymmetric or not? Okay, because if alpha is immediately precedes beta, then it is not possible for beta to be immediately precede alpha. So it is yes. Okay, let's go to the R2. So is R2 reflexive or not? Okay, there's another problem for Elizabeth. So it will be for R. RAB in R. If AB is in R, then A. Oh yes, you're right. I'm sorry, there's a typo here. Thank you. So let's go to the R2. We have reflexive, and most ones say no. Okay, thank you, Elizabeth. So the answer is no, because no letter can be before, no letter can come before themselves. Then is R2 or irreflexive or not? Yes, right. The same. It is the same reason with the previous one. So then, is it transitive or not? Okay, yes, it's right. So use these same examples. AB is in R2 and BC is in R2. AC is in R2 because A comes before C. So AC is in R. So yes. And finally, antisymmetric or not? Yes, that's right. Because if alpha comes before beta, then beta cannot become before alpha. Okay, we're done with this problem. There is a similar questions about in this question about there is a similar questions in the homework, and we don't need to prove it, but I suggest you to write a simple explanation. So why they are have this property or not. Okay, let's go to the next question. So in this one, to prove these properties, then please use 2 minutes to think about it, and then we'll work on it together. Okay, Everyone asks, can something be neither reflexive or irreflexive? And here is an example. So the set is A, it has three elements A, B, C, and in R, AA is in R, BB is in R. Then this one is not irreflexive because we don't have CC in R. But it is also not, it is not reflexive because we don't have CC in R. But it is not irreflexive because AA or BB is in R. So for these relations, it is neither reflexive or irreflexive. You're welcome. Okay, let's get started with this problem. First one, we need to prove the relations is reflexive. So if it is reflexive, then we can let an element, let a z from the integer set. And we need to show that ZZ is in R. So this is the definitions of reflexive. So we choose a Z from the integer set, then Z minus Z is equal to 0, which is divisible by 3. So ZZ is in this relation. Thus, R is reflexive. Okay, any question about this problem? I think no. Then we need to prove this relation is symmetric. So we can still let AB is in R. Then A minus B is divisible by 3. Then A minus B is equal to 3m, where m is an integer. This is by the definition of divisibility. Then we can multiply both sides by -1. So minus A minus B is equal to minus, it is when n, we substitute n with we substitute minus m with n. M is also an integer. This is by the closure property of integer. So B minus A is divisible by 3. This is by the definitions of divisibility. Then we have BA in R. So we proved if AB in R then BA in R. So the relation is symmetric. Okay, let's go to the next question. Prove R is transitive. So we can let AB in R and BC in R. So A minus B is equal to 3m, and B minus C is equal to 3m, and n is an integer. This is by the definition of divisibility. And if we add both sides, we have these equations, and we can cancel the B. We have A minus C is equal to 3m plus n. And 3L. L is equal to n plus n, and L is an integer. This is by the closure property of integer. And then we have A minus C is divisible by 3 by the definition of divisibility. Therefore, AC is in R. So we proved if AB and BC in R, then AC in R. So this relation is transitive. Okay, any question so far? Let's go to the next one. What's the partition of integer set induced by the equivalence relations of R? So in this one, we always find that there's a property. This is divisible by 3. So by division theorem, any integer from Z, any integer, we can write it as 3k plus R. 1k, well, k is an integer, and R, it is equal to 0, 1, or 2. So if we choose 2 integers whose remainder are the same, then the difference of it is always divisible by 3. This is the main idea to solve this problem. So we say this relation induces a partition P0, P1, P2 on the integer sets, where T there is equal to the integer such that is equal to 2k. K is also an integer. And the P1 is the integer that its remainder is 1. Okay, here is the problem from Peter. What about a positive and a negative integer? So m can be either a negative or positive integer. These partitions can be applied to all the integer, whether it is positive or not. Okay. Yes. Yes, the remainder would work in the same way, no matter it is negative integers or positive integer. Okay, let's go to the combination problems. So this is a long problem. Please read it and think about it for 2 minutes, and then we'll work on it together. So let's make some notes on that. Best of 5 means that either the player A or B wins more or equal to 3 sets. And A and B is that, for example, if we have the sequence, the ordered list like this means the A wins the first game, B wins the second game, A wins the third game, so on and so forth. Okay, here is my hint. And you can do it by yourself for 1 minute. And when you finished it, please type your answers for A in the chat. Okay, there are 2 answers in the chat window, and let's use more than 10 seconds to see if there's more answer. Okay, let's think about it. So if we want the match end after 3 games, means that we have a winner after 3 games. And the best of 5 means A or B has A or B wins more than 3 sets. So it can be either AAA or BBB. AA means A has won 3 games, so A wins. And the BBB means B wins 3 games, so B wins. So the answer is 2. So we have 2 ways. Which are either A or B. Okay, let's go to the next second one. So how many ways are there for player A to win in exactly 4 games? So you can type your answers in the chat windows, a number to show how many ways, and or some ordered list to show how A wins. Oh no, that means. So there's a question from Peter. Is this counting match that ends at 3 games? So no, we just count that it ends at the 4th games. Okay, Moses. Okay, that's answer 3. Yeah, that's right. So if we want it to win in exactly 4 games, then we need to require the 4th game. The 4th game should be won by A. So no matter what's so A must win 3 games to win the best of 5, and it should be win in exactly 4 games. So A should win 3 win 3 in total, but he should win the last one. So we needed to choose 2 to put A in. So we can put it as A, B, A, B, A, A, or A, B. So we have 3 ways. And the 3 ways are A, B, A, A, B, A, and A, B, A. So this one is very similar as we needed to choose 2 from 3. So 3 choose 2. That means we have 3 seeds and we should choose 2 seeds to put A on. Yeah, so it's 3. So another student say, can it be 4 choose 3? So no, because this one should be fixed. If we use 4 choose 3, then we can give 4 seeds and choose 3 of them. Then then this game will end at the 3rd game. Yeah. So the C should be 3 taken from exactly 2. Okay, let's try the next one. They are quite similar, but you can try it by your own and see if you have understand the previous one. So firstly, please tell me how many ways are there for the player A to win in exactly 5 games? And then please tell me is which choose which. Okay, thanks Peter's and Andrew's answer. So yes, it is 4 choose 2, and the answer is 6. And the same with the previous one, we need A to win in exactly 5 games. So the 5th game should be A. So the A is fixed. So we have 4 seats and need to put 2 A's on. So it is 4 choose 2. Oh, okay. Another one is 4 choose 2. So 4 choose 2 is equal to 4 times 3 over 2. It is equal to 6. Any question on this problem? Okay, let's go to the next one. So please use 2 minutes to think about it, and then we'll work on it together. And when you're done, you can type your answers on the chat window. Okay, there are several informations contained in this problem. Firstly, the committee should be 7 persons. So the number of seats should be 7, and then there totally have 20 persons. So so we can choose 7 seats from 20 persons. And also we have a condition or constraint. Okay. That is the 3 members, Mary, Sue, and Tom, must show together. So there are 2 ways to form 7-member committee. That means two cases to form. The case 1 is that the 3 people is on committee. And this is the answer. This is the answers from Peter. That means we have already fixed 3. We have already fixed 3 of them, and then we need to choose another 4. So it is 17 choose 4. But we also have case 2. That is Mary Sue and Tom are not on committee. That means the 7 of them are not decided yet, and they are not on the committee, so it is 17 choose 7. So we need to analyze this problem from 2 cases. So the total is 7 choose 4 plus 17 choose 7. Any questions so far? Any question about it? Any last minute question before we wrap up? Okay, then thanks for coming to this discussion section. We are end for today.